Hello everyone, this is a video about homework 1. The due date is here, the 30th October, and we have basically just a single question. But, of course, it has its sub-questions, so let's dive into it. Now, the task is to create a replica of step function that is already available in the control system toolbox. But here, instead of just returning the y and t values based on the step response GS, what you should do is implement differential equations solving methods in this function. So basically we call step GS and we get y and t. It should work like that, but we will use our own code for solving the differential equations. Of course, our input to this differential equation is just 1 because we're using step. So that's kind of easy or simplifies the step or the whole algorithm, because we don't have to deal with the time-dependent input type of things because it's just 1. So, and there are different methods, and each method will be graded here. You can see 5 points for control system toolbox step function. So inside this function we will still, for comparison, call the step function and return y and t if the method is equal to default. By the way, we will plot all the different methods: the control system toolbox, the midpoint method, the HW1 method, the Runge-Kutta method. They will be just plotted on a single plot. Therefore, in parentheses, you can see that the method should be named default. If I pass in default, it should use the control system toolbox's step function, and its color should be black. Stands for K. And if we and you should also implement the midpoint method in solving the differential equation that corresponds to that transfer function. And if I plug in midpoint in this method, basically this one should be invoked or returned. So basically don't forget that you are also returning the response. So if I'm providing a certain method, it should basically return that result corresponding to that method. So yeah, if I provide midpoint, it should be returned. That one should be returned. If I provide HW1, that one should be returned. If I provide Runge-Kutta 4, for example, and then the Runge-Kutta method should be returned. So basically there are 3 different differential equation solving methods and the control system toolbox. Of course, this is already available, so 5 points for that. But the focus here is on the midpoint HW1 method and 4th order Runge-Kutta method. So these are basically most of the time just for dx equals or dy equals something times y plus. There's also not even the plus part, but you can work it out. If you look close to the implementation, you will see that it is possible. By the way, you can use the control system toolbox for your help in order to convert this transfer function into the according differential equation. First order differential equation, kind of, but keep in mind that this is a special thing in control theory. It is called the state space representation. So you have the state space representation, and there are functions that help you out in converting transfer functions into state space representations. Now, the main point here is to work out a way of combining the state space representation and the differential equation solution methods, solving methods. So there is a connection. You can just directly use it, but you should work out how. You can see there are certain colors. Please don't change the colors. Stick with the colors. Stick with the method names. And other than that, you will combine all the methods on a single plot using the assigned colors and showing their names in the legend. So these names will also pop up in the legend in the plot. And the plot will be generated internally, so we are going to code this function, and in this function always there will be created a figure that has all the solutions on it, but returns only the methods one. And then a quick comment: once you have done all this coding here, which method performs the best and why. There's this question here. Add your response as a comment and I'll show you in a minute how. There's, by the way, a step size already defined. Don't change the step size. Use h equals 0.1 for all the methods that are possible. Here in the control system toolbox, of course, you can just stick with the transfer function step response. But other than that, you should use the step size here. You may use the step info in order to create a reasonable time vector, because you will need it. So you can just use step info and the data in step info in order to create a t vector, time vector. Your sampling time is already given, h equals 0.1, but your final time can be calculated based on the step info. So yeah. Now, in terms of submission, you should only submit a single .m file. And I'm going to show you that M file because I have already prepared a template for you. So no PDF file, no Word file whatsoever, no picture, handwriting whatsoever. Just a single .m file. Other ones will not be accepted at all, because I'm going to run this M file and just quickly check your code. So it's and I've already provided to you also a main function part or main code part that is also not going to be submitted. Only submit the M file that is requested. Yeah, everything will be tested. Each late day you'll deduce, or your grade will be deduced 10 points, and of course cheating is not allowed. Don't copy and paste your code, and don't share code with your teammates or just classmates. Now, this is going to be the file and function that you are going to submit. Upload only this file. If you look at the commands, it should be helping you out. So there's this default method that uses the control system toolbox, implemented here maybe, and then you will have the midpoint that is going to be implemented here, the HW1 method here, Rungerkutta here. Once you have computed everything, you might want to combine the plots here. That was this question here that requested all the plots on a single figure, and then maybe return the result that is necessary, or that is described by the methods here. You can, by the way, append your command here, which method performs the best and why, just some comment here. And then you might want to use another file, main.m. This was step-response.m. This is main.m. In your main function, you can just test it for different transfer functions and different methods, and you should get the certain result here. So I'm going to also give you these files. You can see I have already prepared the same file here. I'm going to upload it to Ninova so you can download it. Just alter this or update this function with your implementation and post this function, nothing else. Don't put any, sometimes some students like to do things like this. So there's a function and then there's a piece of code. Please don't do this in this case. Do it if you want to test your code, but when you upload it, please get rid of everything. There should be just a function in it, so I can call this function over and over again, because I will use the computer assistant here. I have a certain MATLAB code that I've implemented. It will just download all the Ninova data, copy your individual student ID corresponding file, test it, and then just go to the next student. And if you do some alterations on this function, that might prevent my code, so please don't do it. Just update the implementation goes here, pieces of this, and nothing else. And response goes here, of course. So only upload this step-response.m file, nothing else. This is the template. Download it, fill it in your implementation, and upload it back to Ninova. You will have access to this. Maybe you might run this main.m file, which calls the function to test your algorithm if it works or not. And that's basically it. Hope you will enjoy it and hope that you will learn stuff doing your homework. Good luck.